Hello, my name is Andrea Codd and I'm going to talk about 3D multi-resolution gravity inversion with both point and gridded anomaly data. And this is work I did with Lutz Gross. The goal of any inversion is to take data and use it to work out ground properties in the subsurface. In this case, we are taking gravity data on the ground and using it to get density in the subsurface. The more data you have and the better the resolution of the data, the more likely that the result is going to be better. And because we want to look at big problems, we want the algorithm to be scalable. If we double the data or double the problem size, it's okay to double the compute time, but not increase compute time inordinately. And if we increase compute power, we want to decrease computer time. We want to be fast. For point data, we have two additional goals. We want to locate the data exactly in the mesh, and we want to be able to compute gravity exactly at those locations. To make sure we have the best possible performance for our problem size, we have chosen to use an unstructured tetrahedral finite element mesh. This means that we can vary the mesh size within the domain and have a really fine mesh in part of the domain we are interested in and a much coarser mesh away from the data and ground surface. The edge of the domain is very coarse. For the Kalgoorlie example, we had data from Alan Atkin at 200 meter resolution. So we chose an element mesh length in the data area to be 200 meters, and the element size at the edge of the domain were 32 kilometers in the ground and 64 kilometers in the air. Any inversion method has a forward model, and for our case, it is the relationship between gravitational potential U and density, represented here by ρ0 m. ρ0 is just a reference density. It can be defined to be 1 in the subsurface and 0 in the air layer. Alternatively, it can include depth weighting, which varies ρ0 with respect to depth in the subsurface. Our objective is to find m. To find m, we define a functional j composed of two terms, a data misfit term and a regularization or smoothing term. Data misfit is the difference between the computed gravity and the actual gravity in the data region, and the regularization or smoothing term, grad m here, is added to ensure a unique solution for the minimization. Our objective is to minimize J, subject to the gravitational potential U, satisfying the forward problem that I've written here in weak form. So how are we going to do that? The relationship between density and gravity is linear, which means that I can use an all-at-once approach, a Lagrange minimization approach. I set up a really big equation, the Lagrange function, combining cost function J and the forward problem for U, and I minimize that with respect to property function M, gravity U, and Lagrange multiplier. And here it is. After a lot of algebra, I derive one equation that I need to solve for property function m. Because D is symmetric positive semi-definite, I can solve for m using the precondition conjugate gradient method, and I can use the smoothing, the grad m term, as the preconditioner. Once I have the equations I need to solve for m, I discretize the problem with the unstructured tetrahedral finite element mesh. The resulting discrete equations I solve with another precondition conjugate gradient iteration, this time with algebraic multigrid as the preconditioner. So there are two iterations, an outer iteration for solving for m from the Lagrange minimization, and an inner iteration where I solve for the discrete equations using algebraic multigrid precondition conjugate gradient. AMG is fantastic in that a lot of the work that needs to be done is performed on smaller systems representing the big system and not on the big system itself that we need to solve. It reduces the amount of time spent solving the discrete equations, and we use the ESIS eScript implementation that is parallelized, speeding up the compute time. Does it work? Well, here is the answer we got for the Kalgoorlie Boulder region in Western Australia. The first is a density at 500 meters, the second density at 1 kilometer and at depth, and the last is density at 5 kilometers deep. There's lots of solutions, so to check to see if our solution is remotely reasonable, we then check the gravity map. And here is our gravity map. On the left is the input data and on the right is our computed gravity, and you can see the similarities. Our solution is slightly smoother than the input data, which can be seen in the slightly smaller in magnitude values of the gravity. This is expected as we have added smoothing to the cost function. Our goal was always to invert point gravity data without the need to interpolate the data to a grid. Our algorithm we trialled on the Mount Isa Cloncurry region of Western Queensland. In GeoRes Globe, we picked this region as it had lots of different observation surveys. We downloaded the 6,519 data observations from 23 different surveys, each with a different measure of accuracy. The objective was to locate these measurements exactly in the finite element mesh. So each observation point is a node in the finite element mesh, and we refine around these nodes. I have shown the ground level mesh. It has a really coarse mesh in the buffer region and a very refined mesh around the observation points. I have shown a blow-up region, the red square, to show how mesh size varies at ground level. The observation spacings had a maximum of 2 kilometers and a minimum of 0.7 meters, so there was a significant difference in element sizes at ground level. Now, because we need to be able to compute the gravity at the observation locations that are node points in the finite element mesh, we need to reformulate the forward problem as a first-order system with gravity vector as the unknown. These equations are completely equivalent to solving the gravitational potential forward problem. And because we are looking at gravity as the unknown, we also need to have a higher order regularization. And in keeping with the first-order system philosophy, we use a first-order system for smoothing as well. It looks a lot more complicated, but it serves exactly the same purpose as the original grad M smoothing. So again, the idea is we need to find M, so we minimize a functional, which is composed of the two parts, the first, the data misfit, and the second, the smoothing, and where the gravity has to satisfy the forward problem. And we set it up exactly the same way using the Lagrange minimization approach, and using that we end up with a very similar equation for the property function, in this case the property function being P, capital P. Here it is. After a lot of algebra, the equation we need to solve for property function P. The method is the same as for gridded data, the precondition conjugate gradient method. We only need to use the diagonal elements of matrix S, the regularization, as the preconditioner, which reduces computational costs considerably. Once we have these equations, we discretize the problem, and the discrete equations are solved with algebraic multigrid precondition conjugate gradient. Again, with ESA script and the lovely parallel iterative solvers. Does it work? So here is our picture of our density inversion for the Mount Isa Concloria region. It seemed to be a reasonable answer, and we now need to compare it to the actual gravity. So here it is. The top is the data from GeoRes Globe, and the bottom is the computed gravity from our inversion. And to me, they look remarkably similar. There's a small decrease in some of the really high measurements, and there's a small increase in some of the really low gravity measurements, but it pretty much looks very similar to me. The highlights. We have an inversion scheme that for gridded data had roughly the same number of iteration steps regardless of the size and resolution of the data. So grid independent number of iteration steps. Multigrid performed brilliantly, giving the appearance of scaling appropriately both with problem size and compute power. The advantage of the unstructured mesh means we have a fine mesh only where we need it, decreasing problem size greatly from a structured mesh. And we can locate the point data exactly, and we compute gravity at exact locations. No need for any interpolation of either the data or the computed solution. Where do we go from here? Well, joint inversion of magnetic and gravity gridded data would be good. The magnetic inversion for gridded data can be solved in exactly the same way as gridded gravity data. It would also be nice to incorporate adaptive mesh refinement. And of course, we always want to solve bigger problems, more data, greater resolution, bigger domains. The codes are all available on GitHub, ESA script you can download, and all the code that ran the gravity inversion is in Gambit. Thank you.